Hi, I'm Dr. Liam Brittle, and you're watching the Challenges and Opportunities in Graphene webinar series from the University of Manchester. Today we'll be hearing from Dr. Nic Gowland, Business Development Manager at the Graphene Engineering Innovation Centre. Nic will be talking about graphene and 2D materials for orthopaedics, including hip replacements, tissue engineering and surgical tools. We also have Application Manager Dr. Craig Dawson talking about dental implants, and Jason Laing, CEO of prosthetics firm Promake, on some of the game-changing benefits of graphene in the next generation of smart prostheses and lightweight surgical casts using advanced 3D printing technology.
So we've got what I think is going to be a very interesting, diverse seminar online today. We're beaming to you from both live at the Geek as well as distributed amongst various people's homes, including Nic's living room. So I'll introduce Nic. We've got three speakers today, but so Nic's background is different from a lot of the rest of us at Geek, is in biological sciences. So he's completed his PhD at the University of Leeds all the way back in 2010, studying mechanical and biological properties of novel joint replacements. So it puts him in good place to speak to us today on the current topic. He's worked in business development and industry at places like Bunzl Healthcare, working in primary care, and then in surgical sales as well. Before coming back to the university, coming to the University of Manchester in the medical faculty, and then back in 2008 joined us in Graphene at Manchester role, where he's bringing companies in to explore new areas of graphene research and development collaborations. So we've also got Dr. Craig Dawson, who will be talking about graphene composites and dental implants based on a project from a number of years ago, and Jason Laing from Promake, who's going to give an overview of limb prostheses and possible advancements using graphene. So with that all said, I'll hand over to you, Nic, to take it away, please.
Yeah, cheers, Liam. Thanks everyone for coming to this webinar. A little bit different in that it's in orthopaedics, it's in a medical setting today. But hopefully what we can get out of this webinar is some opportunities for graphene companies, maybe for orthopaedic companies, and generally some interesting ideas for entrepreneurs or new product development people to take forward. So I've called it 2D materials. In honesty, most of what I look at, or I think all of what I look at, is graphene. It's obviously the most advanced in terms of these application developments, but yeah, maybe the title should have been a bit different. So can you all see the big screen? Yeah, is it just showing the single screen? Good. So what do we mean by orthopaedics? So orthopaedics is a branch of medicine dealing with bones or muscles. So anytime a surgeon corrects a broken bone or takes out a hip, puts in a hip replacement or adjusts some sort of bone deformity, that is orthopaedics. And typically orthopaedics is this sort of setting. So what you can see is someone having some sort of orthopedic procedure done on the table. It looks like a hip replacement. If I just put my pointer on. So these sort of things you see here are the kind of shells they use for sizing hip replacements. They have various tools and reamers. And what we do when we see this sort of setting is you think, what is the opportunity here for innovation and for new products? So they've obviously got hardware and tools here. They've got breathing apparatus. They've got a lot of PPE. There's lighting products. There's screens there. There's various drips and things. So from a business development point of view, working at the Geek, I like to look at this and think, what is the opportunity here? So, I mean, the big opportunity for orthopedics is the industry size, of course. An orthopedics market is worth about $50 billion a year. It's broken down into mainly hip, knee, and spine surgery. So these boxes kind of represent the share of that 50 billion. So trauma fixation is another large part of it. So trauma fixation is when you fix a broken bone. Also arthroscopy, which is imaging during orthopedics. And there are various other things, niche things like maxillofacial surgery, cranial surgery, essentially anything where we're operating on the bone. And most of what I'm going to cover is kind of in-body orthopedics. But Jason later on is going to touch upon sort of limb prostheses or external prostheses, as I call them. So the first thing I'm going to focus on is hip replacements, but most of what I'll discuss in hip replacements is also valid for knee replacements as well. So what is a hip replacement? I'm sure we've all heard of it, but just to kind of clarify. So a hip joint works like this. You've got a ball and socket, a typical ball and socket joint that works very well. You have a layer of cartilage on top of this ball. And in a healthy body, that ball rotates in the cup very nicely and we move. However, as we get older, or if we undergo some serious stresses to that joint, for example, a car crash or repeated injury from running, for example, you can eventually degrade that cartilage and you get gradual pain, more and more pain until you can no longer use that hip joint. And this is when you get a hip replacement. So what they do is they very simply, they cut off the top of the femur. They also remount this cup, the acetabular cup, and they replace it with a prosthetic. So here is a typical prosthetic where you have this metal ball, for example, you have this stem that goes down into the femur, and then you have this prosthetic cup that replaces your acetabulum. And then once again, you've got a very smooth functioning hip joint, and it takes away all that pain that people had before. Now, hip replacements are probably the most successful surgical intervention ever. There's around 100,000 primary hip replacements in the UK every year, and there's more than 1 million primary hip replacements globally. And when I say primary hip replacement, that means a full hip replacement, but there are other things we can do, like sometimes you can just have a cup replacement, or sometimes you can just replace the head, for example. So it's a very successful, very commonly done procedure, and obviously a huge opportunity for innovation. This is another X-ray image showing a successful hip replacement, just so you can see the way it would fit within the bones. So the first thing I'm going to look at with hip replacements is the materials that they use. So by far the most common pairing of materials is a cobalt chrome ball against an ultra-high molecular weight polyethylene acetabular cup. Just to point out as well, this stem is titanium. Again, there's various reasons why they choose cobalt chrome for the ball, the bearing material, and titanium for the stem. It's all to do with the tribology of it, how well it lubricates, and also the toughness within the bone and where the forces are exerted. So this is the most common pairing of materials for hip replacement. The next most common is the ceramic head against the same polyethylene cup. And then also a growing trend is this ceramic on ceramic. So ceramic head against a ceramic cup. This is every year, ceramic on ceramic is getting more and more popular because the early ceramics were very low wearing, but they had a tendency to possibly crack and possibly get squeaking. But as those issues are being resolved, they're not getting that anymore. So yeah, these are where we are now. Previously, metal on metal was another option, but issues around toxicity, the particles that are generated, means that metal on metal is almost zero now for total hip replacements. So what are the challenges represented by these hip replacements? And for me, the way I work with innovation at the Geek is that challenges represent opportunity. So the main challenges faced by hip replacements haven't really changed since hip replacements were invented in the 50s. You want as low a wearing hip replacement as possible. You're never going to wear a hip replacement down to its core, but as you wear a hip replacement, you get particles generated, and then it's particles that cause inflammation in the joint, and eventually can lead to osteolysis. Osteolysis is where you get loss of bone around the implant because those particles stimulate immune cells to the area and they eventually reduce the bone. So you get loosening of that implant, which is obviously not desirable. And the final thing is obviously to maintain, or if you can, improve the tribology of this joint. So can we make the kind of lubrication that you get there and the strength and the mechanical properties even better than the ones we've already got? So these are the kind of main challenges. So delving into a little bit of research. So first of all, ultra-high molecular weight polyethylene. A very good performing material as the bearing material. But the thing about polyethylene is that because it's always paired with a harder material, either metal or ceramic, the polyethylene is the material that wears and produces wear debris. So what we're trying to do is get this material even lower wearing, even less wear debris. There's quite a lot of research showing GMPs and graphene oxide enhancements of ultra-high molecular weight polyethylene. And the research is quite positive, as with many of these graphene polymer composites. So this top study here, they looked at, again, very low percentages of GO enhanced polyethylene, and they showed around a 15% improvement in Young's modulus and yield strength, a 25% improvement in fracture stress, and no detrimental impact on fracture strain or toughness. So very good improvements in a bearing part that requires very good fracture stress and wear. So looking at wear, this next study, they showed around a 51% reduction in friction and a reduction in wear when applied to an aluminium bearing. So this isn't in a hip replacement simulator. It's a separate bit of research, But what it's showing is that the enhancement you get within the polyethylene by adding GMPs in this case. And both of these studies were compared to virgin polyethylene, pure polyethylene as we call it. The third study in this list is, again, a geo-enhanced polyethylene, higher percentage, so 1% this time. And this study showed an improvement in hardness and, again, a reduction in the wear resistance compared to virgin polyethylene. So again, these are three examples showing really quite significant improvements in the wear properties, which is crucial for hip replacements, and also in the mechanical properties with graphene enhancement. Looking at the ceramics, so ceramics used in hip replacements are typically alumina or zirconia, toughened alumina. Again, there's a lot of literature showing that graphene can be a positive addition to these materials. So a GMP alumina composite showed around a 90% reduction in wear volume and a 68% reduction in friction compared to just virgin alumina. Now that's quite significant. You know, we're getting close towards 100% reduction. You would never get 100% reduction because you can never have zero wear, but this is producing potentially a much lower wearing bearing material. The next study, around a 75% enhancement in fracture toughness and a 25% enhancement in flexural strength. I mentioned previously that fracturing of ceramics used to be an issue, but with enhancements of certain composite ceramics, fracturing is less of an issue. It can still happen, and especially during the surgery, ceramic implants are very delicate. You have to be very careful not to scratch them and not to damage them during surgery. Otherwise, you can then get the fracturing problems that they saw previously. So any enhancement of fracture toughness is obviously an important one. And the final study, so these two looked at graphene and alumina, but as I mentioned, ceramics are moving a little bit beyond just pure alumina. So graphene enhanced alumina zirconia composite showed a 42% increase in fracture toughness compared to the alumina zirconia ceramic material. So again, even in these more complex ceramics, we're seeing improvements by adding graphene oxide. So basically what this slide was designed to show is that there is a huge opportunity for graphene enhancements and graphene composites within polyethylenes and within ceramics, which are the two main materials used in hip replacements. I understand there's obviously longer routes to market, more safety issues and FDA approval and things like that, but the rewards could potentially be huge in these instances. A typical hip replacement in terms of a cost from a supplier to the NHS ranges from £500 for a really bog standard metal and polyethylene hip replacement up to several £1,000s per implant for some of these advanced ceramic ones, for example. So there's a real commercial opportunity there. Before I move on from hip replacements, just very quickly touching on an advanced ceramic material. So the probably state-of-the-art ceramic on polyethylene is called Biolox Delta. So this pink ball you see here is the ball that goes on the femoral head that I showed earlier. One second. Now what this is a zirconia. It's a zirconia toughened alumina with strontium in there, yttria, and also chromium. So it's quite a complex ceramic. The strontium, for example, is added for the formation of platelets in the matrix. These platelets act as a toughening agent. So there's a potential here, you could replace those strontium platelets with graphene platelets. Could we get an even tougher ceramic material? Could we get an even more advanced ceramic? Possibly. It's not been done yet with this material. And clearly this would be a project to collaborate with the company Biolox Delta on. So I just showed this just to kind of show you that the state of the art is maybe a bit beyond the literature I just showed, but there's still scope there, I think, for improvement and for innovation. So that's all I'm going to say about hip replacements for now. I've presented two materials there, the main two materials for hip and knee replacements that could be enhanced with graphene. The next one I'm going to touch upon is GrapheneHydroxyapatite. So again, what is hydroxyapatite? A bit of an introduction. So hydroxyapatite is a naturally occurring calcium phosphate ceramic material. It's present in bone and teeth. And while we think of nanomaterials as a fairly new thing, we think of graphene, of course. Hydroxyapatite is a good example of a nanomaterial that's been around for decades, hundreds of years. It's relevant to orthopaedics. The way it's used in orthopaedics is well, in a few ways, but you see this white coating on this femoral stem. So this white coating is a hydroxyapatite coating. So when this is inserted into the femur bone, They typically don't really use any fixtures or cement because the strain of the pressure of the body holds it in quite sufficiently. But this hydroxyapatite coating then encourages bone growth around the stem so that you get the stem nicely embedded within the femur. But you can also get hydroxyapatite in foams or in powders as well to kind of fill in bone voids. Obviously, bone heals anyway, but hydroxyapatite is a very bioactive material that helps encourage that bone regeneration. However, so it's a very good biocompatible material. However, the mechanical properties of hydroxyapatite are limited. It's not great. And what that means is that its application in some parts of the body can be limited as well. Also, it's quite delicate. It could easily scratch off the substrate that it's placed on. And generally, it's not a great mechanical scaffold. So the theory here is, can graphene improve the mechanical properties of hydroxyapatite initially, but also there may be scope to improve its osteoblast bioactivity. And I'll explain what that is on the next slide. Not on the next slide. First of all, we'll look at the mechanical improvements. So again, there's quite a lot of research on graphene enhancements to hydroxyapatite. There's quite a few patents as well already, but as far as I'm aware, there's nothing on the market or coming through commercially. So the first study we came across showed that graphene oxide enhanced hydroxyapatite had an enhanced adhesion to titanium. So I mentioned that coating on titanium. Sometimes it's powder coated, it could be spray coated. That adhesion is quite delicate. So if we can enhance that adhesion on titanium, what you've got is a more durable and essentially a more effective bone regeneration implant. And this study showed about a 3 times improvement in adhesion to titanium with the graphene enhanced hydroxyapatite. Another area is corrosion. We don't really think of corrosion of ceramics, but of course it does happen, and it can happen in bodily fluids especially. Bodily fluids are quite an extreme environment. But again, graphene oxide enhanced hydroxyapatite showed enhanced corrosion resistance. I couldn't get the exact figure on this one because I couldn't get past the abstract, but they claim to have enhanced corrosion resistance in simulated bodily fluid. Separately on mechanical properties, as you can see here, a study showed around an 86% increase in fracture toughness and a 40% improvement in elastic modulus. And again, this was compared to pure hydroxyapatite. And this was an interesting image showing the formation of these graphene, these grain boundaries within the hydroxyapatite. So this graphene is thought to restrain the growth of the grains within hydroxyapatite, meaning that you got those improvements in fracture toughness. And the toughening mechanisms were hypothesized to be things such as crack branching, crack bridging, and crack deflection. Very similar mechanisms to the strontium that I mentioned in the previous ceramics, as it happens. So again, lots of literature showing very effective mechanical improvements of graphene on hydroxyapatite. But probably more impressive is the bone, the kind of bioactivity graphene can impart. So osteoinduction is basically the kind of recruitment of cells to grow bone. So you think of osteo, always refers to bone. Bone is maintained using 2 cells mainly. So osteoclasts break down bone and osteoblasts build bone. Think of the B in blast as building cells. Now what has been shown quite a lot in literature actually is that single layer graphene or graphene materials has been shown to be an excellent scaffold for osteoblast, so these bone building cells, and also MSC. So these are mesenchymal stem cells, and these stem cells are what become osteoblasts. So graphene has shown really good recruitment of bone building cells and precursor bone building cells, which is a superb environment for bone to be rebuilt, of course, when you get in those cells. There's also strong evidence showing that graphene materials can enhance existing scaffolds in terms of their osteoblast proliferation. So you can add graphene to existing scaffolds, hydrogel scaffolds, for example, and you get improved osteoblast proliferation, which is the multiplication of cells, and also recruitment to the site. So a very effective bone building material. And in addition to that, they showed that significant enhancement of calcium deposits when you have graphene oxide hydroxyapatite compared to pure hydroxyapatite. Calcium deposits are what you need, and that resulted in of this bone-like apatite. So when you combine those things together, you get improved mechanical properties of hydroxyapatite and improved osteoinduction. It's quite clearly, a nice recipe for bone regrowth. This final study, I thought, just kind of visualize what I'm saying quite nicely. So what you have here is an animal study. So I think this was done in rabbits. They make a void in the bone. And as you can see, this is a non-treated sample. So after the void in the bone and they leave it, I think for 2 weeks, you see that void is still there. You then treat this bone with hydroxyapatite, or in a separate sample, a hydroxyapatite treated bone. This is where you see NB. So this square is taken from here. You see new bone here, and you see new bone there, and also new bone there. With the graphene oxide hydroxyapatite, you can see, even on the image, a huge amount more new bone growth, which is quite impressive. And then when you look at the data as well, there was a significant enhancement in new bone formation compared to the non-treated and the hydroxyapatite treated control. So for me, this is a really interesting area. It's something we're quite interested to do at the Geek. We of course have ceramic capabilities at the Geek, and potentially, taking hydroxyapatite and bone regeneration to the next level. I know that Jason will touch upon that as well later on. So yeah, that'll be interesting. Just checking, Liam. Are you letting people in? Can you see people coming in? Yeah. Okay, so that's graphene hydroxyapatite. The last thing I'm quickly going to touch upon is something that I used to try and sell for a year, so I know it pretty well. That's surgical power tools. It was an interesting year. So this is a typical surgical power tool. As you'd expect, it's used to cut bones. So when you do a hip replacement, you're cutting that femur with a very powerful saw. You're reaming out the acetabulum with, essentially, imagine a spherical cheese grater that spins around at very high rates. These are very high performance tools used by surgeons. But again, as with any product, there are challenges, and it's these challenges that present opportunities. So one of the challenges is high temperatures. So you get high temperatures at the bone blade, you can get burning of the bone, you can get necrosis of the bone and the soft tissue around it, which you don't want. The unit itself can get very hot. This is a very well sealed unit, because obviously it has to be waterproof. And as they're moving towards battery power, so heat management in the battery as well is key. The move towards lithium ion battery power is another challenge, but also moving towards more dense ways of generating power, of storing power, but also user control, the weight of it, and also sterilization. And I think for all of these, there's a potential graphene opportunity. So I mentioned cooling as the main, thermal management as the main challenge. There may be opportunities to introduce graphene materials to these blades, whether as channels on top or within the structure. Because if you can take heat away from this blade tip, you will get less burns, less necrosis of the bones, less complications, and much better outcomes. So this is one area, spreading heat away from the tip and away from the blade generally, cooling the whole unit. So sometimes when they're cutting through a big femoral bone of a big guy, they could be cutting for over a minute of it non-stop, moving back and forth at about 13,000 cycles a minute. So it's a very, very intense process going on. So these units can get very hot within a surgeon's hand, and it can also compromise the electronics within them. So there may be ways we can better manage that heat as well. And the obvious outcome then for the product is that a better performing, longer lasting tool. And then battery cooling as well. So these tools are moving more towards battery power, away from pneumatic and mains power. And again, there are issues around thermal management, but also, can we make these batteries more energy dense? Can we charge them faster? Can we make them lighter? This is a handheld unit used by a surgeon. And when you cut in a femur, you might not need too much control, but when you're cutting through a finger bone or doing skull surgery, you need a very, very lightweight controlled tool. Well, we're speaking about control. So at the moment they use this trigger, a typical sticky sort of trigger thing. One idea is a graphene MEMS device, a very sensitive touch device, the sort of thing made by Atomic Mechanics, spin out from the university. Could that be introduced to give a very, very sensitive control? Again, not for a femoral cut, because you don't need so much control, but when we're talking about spinal surgery, facial surgery, could we introduce that level of control that's not been seen before? An obvious one is lightweighting. So this is a solid piece of metal that's machined from, I think, stainless steel. Can we make that lighter, easier to operate for the surgeon? And finally, sterilization. So this whole unit, which is obviously an electronic unit, goes through the hospital sterilization process. So that's a wash with a detergent. It goes through a steamy, high temperature, high pressure sterilization process. Obviously, the seals within this unit are incredibly critical to the unit lasting. Could there be quite a bit of low-hanging fruit there in terms of a graphene-enhanced seal to make it more temperature-resistant, more durable, and essentially you get a longer-lasting tool with a longer warranty at the end of it, possibly. So now I'm going to introduce a couple of other people. So Dr. Craig Dawson is one of our application managers from The Geek. He looks after energy, but also works in construction. And in this webinar, he's going to talk about dental, so he can do everything really. If Craig is on, are you on, Craig?
I'm here. Can you hear me?
Oh, I can hear you.
Good.
Yeah, so let me just, so if you're happy to talk, Craig, we'll jump onto your slide. Craig's going to talk about an opportunity he worked on around graphene in a dental prosthesis. So over to you, Craig.
Yeah, so this is something I did some time ago. Before I was at the university, I was at a company called 2D Tech, which is part of the Visarion group, with another couple of people on this call, Dr. Arun Prakash and Dr. Andrew Strudwick. And we ran a project. I mean, the project was a Innovate UK funded project on dental prosthesis, or full maxillofacial reconstructive surgery. And the reason we picked on prosthetics rather than on orthopaedics was pretty much just the quicker route to market. You need less of that FDA approval that Nick talked about earlier. And but we were looking at moving into orthopaedics, so the objective of the project took that into account, and we were looking to match the density of a PEEK, so polyether ether ketone, which is a high spec engineering thermoplastic, and match that more closely with the density of a patient's bone, the strength of a patient's bone, and the hardness of a patient's bone, in order to extend the lifetime of a prosthetic and of an orthopedic once it's in situ. So at the time, the lifetime was about 15 years. So that anybody that had undergone that reconstructive surgery would probably, in a kind of, might need that surgery again within their lifetimes. And what we were hoping with the project, that we would widen the envelope of possible materials used for that to a point where it would last the lifetime of the patient. So it could make a real significant difference to that specific procedure. And the reason that the company uses PEEK is because it's lighter weight. It's a very, very good engineering thermoplastic, but it has low density. So the PEEK itself can wear out quickly if the bone density of the patient is too high, which pretty much means that you can't use PEEK. So you could only use this PEEK for a certain low number of patients. And we were looking at widening that envelope out by the addition of graphene. So the challenges really were more around the compounding of the graphene into the polymer rather than the end use. So the company we're working with, Eva Dental, which is based out in Cheshire, they use a 5-axis mill to mill out basically the patient's jaw, which is reconstructed quite accurately to their previous bone. And we got to a point where we did widen the envelope, but not quite enough. Fairly low loadings of graphene. But what we did see is that we could color over the graphene in the PEEK. So graphene, when you put it into a polymer, you can have it in any color you want, as long as that's gray. But we found that we could color over that by enameling over the prosthetic. And like I said, whilst it gave a wider materials choice, it wasn't kind of as wide as we were hoping. But that, I guess if we were moving forward in that area, we might look to add more composite materials in there to kind of maybe tailor their bone structure more closely with that PEEK nanocomposite. And the main thing at the time for us was that we got further collaboration between ourselves and Victrex, working on some of these PEK materials, and I believe that 2D Tech still have an ongoing program with Victrex on looking at some of those types of material. Thanks, Nick.
No problem. Cheers, Craig. It's another nice angle on it. So following on from Craig, we've got another speaker as well, which is good. I think just to add a bit more depth to this is Jason Laing from a company called Promake. So Jason's working with the Geek through the EIDF program actually currently on things which involve prosthesis but external prostheses. But I won't give any more intro, Jason. If you're there,
yeah, all good. Yeah,
if you're there. I'll hand over to you and let me know when you want to flick through slides. But cheers for talking on.
Sure, thanks. Hi everybody. As you can see, I'm from a company called Promake International. We have offices both in South Africa and here in the UK. Working closely with the Geek has opened a lot of opportunities for us. So one of the areas that we work in is obviously in the orthopedic sector. And as you can see, if you can take us to the next slide, please, Nick. The current state of how prosthetics gets done traditionally is obviously taking a mold of an amputation area. Where you take a mold, take a plaster cast, use that to do an overmold in order to be able to create the construct for the lock liners and the rest of the prosthesis to be able to fit. Now, the problem with this is obviously the time that it takes and the skill sets that are needed in a very short space of time can sometimes be a hindrance on getting a patient an emergency-based prosthesis. So we try to work around this and decided to develop a polymer and link it to our digital systems. Can you take us to the next slide, please, Nick? So what we're now doing is, a lot of you probably have seen stuff like this before, where we 3D scan the stump and then actually able to mirror from one leg or one arm to the other side so that you get symmetry in length and geometry, so that we are able to go from that stage to our additive manufacturing or 3D printing machines. So this, obviously, once we add the graphene to our polymers, which we've now developed or busy developing a new polymer with Geek, it changes the game completely, because it's almost like a molecular form of carbon fiber that is biocompatible, and you can actually make it a lot stronger. You don't need to make it as dense. So thus being able to make a prosthesis that is cooler, stronger, and can also put sensory devices into it. It opens a massive door for us. So the fact that we're able to combine graphene with the polymer is pretty much a world's first in the commercial aspect, because we're able to now be able to feed this through the 3D printing machines, which has never really been possible before. So we've done a lot of research on this, and the outcomes has been the fact that the graphene itself and the polymer has made this material so strong beyond what we were actually even expecting. It competes completely with carbon fiber, but from a cost point of view, it makes it realistic. So with the beauty about this is by being able to add sensory devices to it, we're now able to change the game completely, because as you can see in the picture here, like a runner, the explosive power coming from the abled leg, or the good leg, essentially, has its own power load or power release. So how do you match that to the exact same power or explosive power in the prosthesis itself? The beauty about with the process, we're able to now then adjust the graphene polymer and the way we do the design around generative design, so that the explosive power coming out of the prosthesis matches the same explosive power of the abled leg. So for a professional athlete, they're getting symmetry in motion and power release, which has never really been able to be measured before. We're now able to do this, and where we're taking it further. So whether it be for an athlete or just an average daily activity, or someone of elderly age, we're able to adjust as it goes. But what we're also then doing is the problem with the normal prosthetics today is when you go through the molding, you put onto the patient, you have molded to that patient as they stand at that very moment in time. So we decided to create a polymer that can be fitted same day, like you're almost going for a measurement on a pair of shoes. So by doing that, we're able to do same day fitments for rural areas where the patient goes in and gets molded there and then by warming it up, and we're then able to create it with different processes to make it stronger, but also cost effective as a stock standard small, medium, or large type prosthesis that can be fitted same day. We obviously going through a lot of research to make the graphene polymer itself extremely strong, but also so we can make it electroconductive, so that we're then able to do ultrasound fixing for broken bones. So we create, as you can see in the picture there, a very lightweight type of brace or cast that the person can wash and bath and clean with. So from a hygiene point of view, it works exceptionally, and also to keep the patient cooler. I mean, especially like with myself, I originally come from South Africa, it gets really, really hot wearing a cast, where now with something like this, it's a lot cooler, it's a lot thinner, you can wear it under your clothes. So it's a lot more compatible to daily living, and it can be fitted within minutes. So this is the type of fixtures and bracing type systems that we're going to be using. We also then, by having a conductive brace, we're then able to run electrocurrent through it, a micro electrocurrent, shall I say, through to, which as you see in the next slide, is with an osteogenic bone matrix, where we're now doing research on putting the graphene into our osteogenic bone matrix, so that the graphene brace itself can actually now electropulse the conductive electrobone pace. And as you saw with Nic's previous slides, how it increases the osteoblasts, so that we are then able to increase the speed at which the bone will knit and join, and the strength of it. And should they get any atrophy or bone resorption over a period of time, which it sometimes does happen, especially around prosthetics, like if you look at what Nic was saying around the hip implants, a lot of breakages or breakouts are due to the bone getting atrophy, essentially, to a degree, in layman's terms. So being able to put this around a female implant, we can then electropulse the bone again and reintroduce the osteoblast regrowth. So by using the two compositions of 3D printing, additive manufacturing with bone paste, the opportunities are endless. So we're able to 3D print scaffolds that are biodegradable with the graphene in it. So we end up leaving the graphene behind and then electropulsing it again through the skin. So should a patient have surgery, later on we're able to then re-strengthen the bone if we notice that there is atrophy happening around an implant, to stop the bone from breaking before the implant pushes through, shall I say. So that's what we are trying to do. We're doing a lot of research around that. We're working closely with the UK Space Agency on this, as well as the European Space Agency, because it's something that astronauts experience when they've been in space for too long, when they come back on the forms of osteoporosis. So being able to do this type of research and combining it all together, we're now taking analog and digital and merging it together. So we're expecting medical science to really improve quite drastically once this hits the commercial market in the near future. Thank you. Thanks, Nic.
Thanks very much, Jason. So that's the end of this webinar. Over to you, Liam, if there are any questions or anything.
Sure.
Thanks everyone for coming. Appreciate it.
Yeah, and thank you again to all the speakers, Craig, Nic, and Jason. That's been very, very interesting. I've not seen huge amounts of questions coming through, Nic, but we've got one from Steve Bennett asking about whether Geek is doing work with Lucidian, previously known as the British Ceramic Research Association.
I mean, you can add on that as well, Liam. I'm not aware of us working with them, but it's probably someone we should be working with. We're starting to do a bit more ceramic work at the Geek. We've had our first ceramic project signed off recently, so it's a good point, Steve. Probably someone we should connect with, and I imagine you can connect us, Steve.
Hi, Nic. Yeah, I'm sure I can.
Well, you do well. But that's a good suggestion. Probably should.
No,
yeah, because they've moved their work away from, I mean, they're based in Stoke, but they've moved their work away from being sort of traditional potters, in that makes sense, in the same way as the ceramic industry has had to move. So there's probably quite a lot of technology and advancements that they're involved in that might be some mutual, opportunity.
Do they do medical grade ceramics? Do you know?
They do. I mean, they've also been doing, I know in previous years, they've been doing sort of automotive and aerospace ceramics.
Interesting.
Many, many years ago, they were looking at producing a ceramic engine block.
Okay.
I don't know where that's gone. I've not been in touch with them for a while, but I'm sure as an organisation, they'd be fascinated by this presentation.
Yeah, no, I'll definitely follow up with you on that.
So, Nic, I've got a question for Jason, I think, from Matthew Smith from Reuben Ellis.
Hi, thanks, Liam. Hi, Jay.
Hi.
Yeah, sorry, I'll put my video on so it's not so.
It's all good.
Hi. Yeah, I had a question about the bone graft section on your final slide there. I was just wondering whether you make those porous so that maybe you can load on like pharmaceutical actives or anything like that into them.
So essentially, currently, it's almost in a paste form that we're doing right now. Okay. So we've got multiple applications that we're working on. So it's almost, you can almost inject it with like a syringe, essentially activated in theatre. Because obviously the lifespan, you've got to time it perfect. So you activate in theatre and you can actually inject it directly in theatre itself. But what we're currently doing now is we're creating porous scaffolds with the graphene, we're going to be doing with the graphene lattice in it. So that we then can then obviously induce osteoblast through the scaffold itself. But obviously the porosity of the scaffold has to be to a certain density, else just don't get the right fit. Essentially, it's quite a bit of a merge between maths and science. So it is, we are going that route. We're definitely looking at actually this year still we will be making new sets of test scaffolds that we're going to be doing in lab cases. So yeah, we are going that route already.
Oh, fascinating. Thank you.
We had some research, the guys wanted to do the same with the 3D printing of the hydroxyapatite. But as Nick mentioned earlier, the delamination, the strength of it just wasn't there. Yeah. So this might be something to look at with the hydroxyapatite if people prefer to go that route. But having the bone paste already in play, and we've already got a lot of research and accreditation around the bone paste that we're working with, it will change the game quite completely, because we just found we've got a better link and better knit of the graphene with the bone paste. So this is something, if you're interested, to give me a shout about. Yeah.
Okay. Cool.
Thanks.
I was just going to add to that, Matt. You asked about porous structure, wasn't it?
Yeah, that's right.
Yeah, I mean, obviously the hydroxyapatite that they use on implants is typically porous, and the same with the hydroxyapatite plugs they use to fill bone voids. And obviously a porous structure like that is typically quite brittle as well. So that's another area where you do, those mechanical improvements could be quite beneficial.
Yeah, absolutely. Well, a lot of the work. Sorry, Jay. I'm a patent attorney, so I work in technical fields. But one of the main ones that I've worked in the past is ceramic, like fine ceramics, where obviously control of porosity versus, as Nick says, sort of thermal management and brittleness. That's quite an important thing that they deal with. So it's interesting to see it working in a different sort of environment.
Yeah, I'd like to get your details and chat further. Yeah.
Oh yeah, definitely. I'm actually just down the road from you at the moment, working at home in Sale. So,
oh right.
So nice. Yeah, I'll drop you a message.
Perfect. Sounds great. Yeah. Thanks.
No worries. Cheers.
Thanks, Matthew. We've got a few more questions coming through, and there's one which I wanted to ask as well, Nick, about potential toxicity or hesitancy about putting graphene inside the body. But I got a question from Terence Barkham from the Graphene Council. Terence, would you like to take the stage?
Thanks, Liam. First of all, congrats. It's a really interesting presentation, and I like the mix that you put together. I've got a two-part question. One is, I think it's really interesting to look at the mechanicals that you guys have been really focused on, I think, with these presentations, and just ask a general question, I think, about the potential of adding sensing capabilities, using them in combination. I think that's really quite interesting here and a game changer, as I think was mentioned with the prosthetics. And the other part of my question is, how is this information getting communicated to the medical community? So for example, in the past, I've worked with the International Association for Dental Research, right, which would be an entity that would have a lot of interest in some of these developments. And there's other medical associations that would have a lot of interest in these developments, but wouldn't necessarily know a whole lot about graphene or how to get engaged. So it kind of occurs to me that there's some opportunity here for us to reach out to these verticals in the medical side to better communicate what these possibilities are and bridge those communities. So those are just a couple of thoughts, and any reactions are welcome. Thank you.
Yeah, I mean, I'd agree on the question, I suppose, is how does someone like the geek and Graphene manage to better communicate with the medical community? There is a lot of work going on in the medical faculty with people like Cyril Busey and Kostas Kostarellis, that they've got a big 2D materials in healthcare project with a few big partners, pharmaceutical partners, medical device companies. Obviously, the research there is probably quite a bit more fundamental level. So I think at that level, things are doing okay. I think we could all do, or I could certainly do better at getting these, this lower hanging fruit past the eyes of people in the medical community.
I think, Nick, sorry to interrupt you there. I think one of the things that we found very challenging in that respect, it's not necessarily how communicating it out there. It's also getting people to, from a knowledge point of view, understanding what is possible, because of graphene still in retrospect still seems very new amongst the medical guys, and getting them to believe in what you know is possible when you haven't got sufficient evidence that people can just have access to randomly. That's been our biggest challenge, is obviously getting people aware of what is possible.
Yeah,
I think another point there is on the business side is the length of time to market, and getting somebody who really believes in what you're doing to be able to realize that these things can take time. And Jay, you might be able to comment on this better than I can, but that prosthetics and proving a new material in a prosthetic might be a route to market for a material that's perhaps quicker than an orthopedic. Yeah. But eventually that material can be qualified for orthopedic use as well.
Yeah, we spent a lot of time with the MRHA, or MRH, yeah, and NICE. I've spent quite a bit of time with them, and we've had to really construct it correctly, as you say, in order to be able to follow the procedure so that we have the right flow of market, in order to be able to quantify everything in the right procedure. You can't just go jump from one to the other, because you're just hitting a brick wall. So it's been a big learning curve, yeah.
And Jay, again, can you comment on potential funding routes for that? You know, it's not something that as a technologist I tend to go down the kind of Innovate UK route, but there are plenty of NHS kind of funds and other medical funds available for these this type of activity.
Yeah, so that's why we've gone the route a lot on the space side of things. We're busy on the process on an activation for a feasibility study, and there's funding around that, as well as we've managed to get to a point of now applying to be able to do research on the ISA space station with this process, because of the bioreactor systems we're working with Kaiser Space. So through that, there's a lot more credibility, because that's so much further down the road on high-tech research. Then to bring it back down, you got a lot more credentials to prove what you're doing. Trying to start from the bottom up has been difficult. So we just said we'll just go straight to the top, literally out of orbit, to be able to then come back and say, this is the tangibility. And then the funding processes and funding incentives have come about from that aspect. But starting from the ground, literally up, has been difficult. So a lot of it's been self-funded to get, and then Geek with the ERDF programs has been assistance. That's been the biggest help to us, really.
If I may say something, my name is Chris. I do funding, and the way I work is I work internationally. UK is actually now becoming the first country where you have the most foreign investment. So there's actually a lot of opportunity. If one of you look for funding for any project, feel free to contact me.
Fantastic. Keep in touch, yeah.
Yeah, I'll let my information on the chat. So
thank you.
Thank you, Chris, and thank you all for that. I think there's been a few questions about other two-dimensional materials in the chat, so I just thought I'd combine them together. So, Nick, you titled the talk "Two-Dimensional Materials in Orthopaedics," but obviously you talked mainly around graphene and graphene oxide.
Yeah.
And I'm just wondering if you've seen any work with things like hexagonal boron nitride, for example, or other 2D materials that might offer other functionality than what you've discussed today.
Yeah, so I think I set the title before I started doing some of the research, and was thinking I'd find plenty of stuff on 2D materials generally. I mean, there is some composite work with hexagonal boron nitride. I couldn't find much, if I'm honest, with it linked to kind of orthopedics as an end application. I couldn't find much in ultra high molecular polyethylene, to be honest. But I'm sure it is out there, and well, I think it's out there, but I think it's probably an area that needs some development now. You know, as we're progressing with understanding those 2D materials, there's a better supply chain for those other 2D materials. Maybe there's some more interesting projects we could do in that area. But yeah, maybe it was a failure on my part. But I couldn't find much. I don't know if anyone else is aware of things that I missed. Adrian?
Okay.
That's why I asked Nick.
Okay.
It struck me that HBN would be a good partner with the ceramics, but I haven't heard anything either. I think maybe just failure of imagination moment on the part of people developing this stuff.
We did some feasibility studies at the NGI with HBN, Adrian, with some dental paste. The work is still ongoing. I'm not sure if it's been published yet, but I know there has been some feasibilities at an academic level.
Yeah, I've heard of HBN being used as a filler, Paul, for dental treatment because it's white, but I hadn't seen it used with these ceramics for bone joints.
Yeah.
Like you say, Nick, there's a huge amount of work to be done in this field.
Yeah, absolutely.
Great. So I think we've probably covered most of the questions. Nick's just posted a link in the chat, which would be really helpful if everyone who's on the webinar could fill in, just to give us an idea of a bit of feedback and see what we can include in future webinars. I think we'll probably draw it to a close there if that's all right. Unless you have any further comments, Nick or Jay or Craig.
No, I mean, you mentioned briefly about the toxicity. I just thought I'd quickly touch upon that because it's a common one. I mean, in none of these areas we can ever say graphene is safe or graphene is non-toxic, because graphene is a vast spectrum, and toxicity is also a vast spectrum of exposures. But there are some studies showing that graphene within the polyethylenes that I mentioned are comparable to non-graphene polyethylenes. So there's no effect on cell viability. There's no added inflammation. So those tests are positive, but again, I think more work needs to be done on those. And I personally think the way around we have to do it is to kind of prove the mechanical or the application benefits first. And then if that looks promising enough, then we'd look at, is this going to be viable as implants? So that's where my opinion is on there. I don't know if, Jason, you have any thoughts? I know you've got some in vivo work there that you presented.
Yeah, look, I mean, we are working on a process that we want to be able to make smart implants utilizing graphene, so that we're able to, once the implant has been placed, monitor the performance, the reaction to the body in real time. So, once a person's had an implant placed, such as a hip implant, and once it's been placed, how does a doctor or the surgeon know over a period of time how it's performing until he goes and has another scan done? So we'll be able to looking to put sensors and live tracking sensors, so that because of the conductivity of the implant, to show in real time over a period of, say, a month, that what the performance is of the implant itself, as well as the way the bone is reacting and the strength of the bone, whether it's the atrophy is kicking in or if there's any issues around that or toxicity around it. And that's what's so great about graphene, with its conductivity, its biocompatibility. There's just so much around it making a smart implant. So we are working intensively on being able to create scaffolds and implants strong enough to be able to hold load bearing through our additive manufacturing process, because it's the only way you can do it, really. And the fact that we figured how to put it through an additive manufacturing machine, it's been a game changer. So that's where we're going right now.
Okay. Nothing more from me, Liam. Don't know if anyone else has anything to say.
I am participating to organizing an international challenge on nanotechnologies that will open in 2021. If some of you are interested to participate, same thing, feel free to contact me.
Yeah, if you put your details, Chris, on the survey, the second link I sent, we'll follow up with you on that, okay? The second link should be working.
We'll do it.
Well, thank you all for spending your time this afternoon with Nick, Jay, and Craig, and thank you all to the speakers again. It's very informative, and I think an area that deserves more attention as well. So thank you all, and look forward to seeing you next time.